Okay, folks, we're going to go ahead and get started. Welcome to the PEARG, the Privacy Enhancement and Assessment Research Group at IETF 123. Congratulations, it's Friday, we're almost done. My name's Sarah Dickinson, and my co-chairs, Siobhan and Alison, are both remote today. This session is being recorded. Okay, so as per usual, this is the standard IETF notewell that you should be aware of with the RFCs, with all the relevant information in them. This is the IETF specific notewell relating to privacy and the code of conduct. And so people are aware there is a new IETF code of conduct, 9775, which attendees are encouraged to read. And as always, be nice to each other. There is also a notewell relating to intellectual property for IETF that attendees should be aware of. As usual, we have all the meeting tips relating to Meet Echo. If you are in this room, please, please, please sign in to the meeting, either by scanning the QR code or by connecting directly through the link in the agenda. And if you're in the room, please use the on-site tool, not the full client. If you're a remote participant with a full client, please make sure your audio and video are off unless you are presenting. And with that, we move on to our agenda for today. We need a minute taker today. If anybody in the room is willing to volunteer, that would be fantastic. Or anybody in the chat. Siobhan, could you post in the chat and ask for a note taker there? I'll come back to that in a moment. We have one update on our currently active draft, which is the safe measurement one. If Gershabad is in the room, he said he was going to be here. If not, I can do that update. I don't see him. Okay. Then we have three excellent presentations today. One on covert tracking on Android, one on an exploit of origins to bypass content blockers, and one on homomorphic encryption. If we have time, we will try and squeeze in a 5-minute presentation on privacy-preserving computation. If not, we will have a full presentation on that at the next meeting in Montreal. Okay, so back to needing a minute taker before we can move forward. Is there anybody in the room? This is a very light job in this session because you essentially need to just take notes during Q&A, not during the presentations. So it's not a full-time job, it's only part-time. We cannot start until we do have a minute taker. Anybody? I see Gershabad now. We're still trying to find a minute taker. If there are any volunteers, please. Okay. Anyone? Channeling my, oh, brilliant, Tara, thank you. That's wonderful, thank you very much. That's great. Okay, with that done, we will start with an update on safe measurement, if you want to come up to the mic. We don't have slides, I think it's just just an update.
Hi, everyone. Yes, so three of us are co-authoring this draft on guidelines for performing safe measurements on the internet, and that's for any internet measurement experiment. Since the last time we met, thanks so much to Sarah for sort of an overhaul of the structure of the draft. Now it's called Considerations for Safe Measurement on the Internet. I just want to quickly say three things that we, just to recap, we did go into last call, but they were pending reviews, and so we're pausing that for now. The three things that will be changing now are adding more information on sort of IP address minimization, anonymization, etc. Second, just wanted to note that the three of us that are co-authoring the draft are sort of more practitioners than academics. And so we received a lot of reviews from the academic community that are also involved in doing ethics reviews, etc., of network measurement experiments, etc. So we'll be trying to onboard an author from the academic community, and if you identify as such and want to collaborate on the draft, please let me know. And yeah, and sorry for the slow movement on the draft in the last 6 months, but we'll move quickly from now on. If you haven't read the draft, please do drop comments on the list. And if you have read the draft and had feedback today, sorry that I'm not presenting an overview, but please feel free to state that now as well.
And that new version was just published today,
Yeah,
wasn't
new
it?
version
So,
up. Like, I don't expect anyone to see it because it was like half an hour ago. So
yeah.
yeah.
So the request at the moment is if the list can review this current version, and we expect there to be at least one more update.
Yeah, before
Potentially, if we can introduce a new author as well, we'd like input from them, and then there'll be one more update, and that's the point at which we would reconsider whether it's ready for working group last call, which it's been through once, but hopefully we can get to that point again.
yeah.
I mean, the goal is, our optimistic goal is Montreal, but we'll have to see how it goes. So,
We'll make it happen.
yeah, okay, all right. Thank you. Thanks
Thank
for
you.
that. Okay, so let me. Okay, if you'd like to come up and let me get this clicker. Okay, there we go. Thanks. So our first talk is on covert web to app tracking via local host on Android, presented by Aniket. So please go ahead.
Thanks for the introduction, Sarah. And hi, everyone. I'm Aniket from MD Networks. Today, I'll be presenting our work on discovering a novel side channel attack that we found that one bridges sandboxed web and app environments in Android through the local host interface. This work was done in collaboration with folks from KU Leuven and Radboud University. So modern mobile and web platforms are designed to enforce strict contextual isolation. On Android, it takes the form of UID-based sandboxing, where each app's run on its own process space. Apps cannot directly access each other's data or resources without going through platform-mediated APIs and permissions. On the web, policies like the same origin or cross-origin restricts how one website can interact with another. Communication across these contexts, say from the browser to the app, requires explicit user intent. This contextual isolation is fundamental to users' privacy. But what if there was a way to bypass these boundaries and a narrow but shared interface exists, the local host interface? But let's unpack how this local host path work in practice. So on most platforms, app can bind freely, browsers can allow JavaScript to connect to it. And this exists for legitimate purposes like testing, debugging, or peer-to-peer fallbacks. But what's interesting here is what the setup enables. So any app can expose a service, any website can silently reach it and across context boundaries. This is an unprotected case of platform design. And the real question is, does anyone actually use it in this way? And to answer that, we first need to understand why this channel often flies under the radar, and despite being openly accessible. That's because it operates entirely outside the scope of traditional platform defenses. It doesn't trigger permission prompts. It's not blocked by browser security models. It's unaffected by the incognito mode or even cookie deletion. Even VPNs usually ignore loopback traffic since it never leaves the device. So what we end up with is a side channel, one that quietly bypasses sandboxing permissions and user expectations entirely. And what we are seeing here is a systemic breakdown of expected differences by the use of localhost. So this brings us back to the critical question again. So does anyone use the localhost interface to reach mobile apps and in doing so bypass both the web and the app isolation models? It turns out the answer is yes, and that's exactly what we found. We discovered for the first time the side channel is actively used by in the wild by Meta and Yandex. Yandex is a Russian company which we found doing so, affecting billions of users globally. Let's take a closer look at how this plays out in practice. In the case of Meta, we saw that the local host-based mechanism was being used together with their Pixel infrastructure. To start off with, let me just walk through the full sequence of the steps, highlighting how this cross-context channel operates end-to-end. Meta apps, particularly the Facebook and Instagram app, quietly runs in the background on Android, even when you are not actively using them. They open specific localhost ports, both TCP and UDP, and listen for incoming traffic from the browser. So now here is where the tracking actually kicks in. Let's say the user opens their favorite browser and visits a website. If the site has MetaPixel embedded, it executes JavaScript in the browser contexts. This JavaScript knows to probe the local host ports, attempting to establish a connection with the Meta apps. At this point, the Pixel script creates a first-party cookie called the FBP cookie. According to their documentation, this is a unique ID for their user's browsing session on the domain. It is supposed to be scoped to the browser and the website domain and not visible to the native apps. But the boundary gets violated in the next step. To transfer FBP cookie to the browser, to the native apps, Meta uses a clever trick involving WebRTC, a browser technology originally designed for real-time audio and video communication. As part of setting up a WebRTC connection, browsers send what's called a stun request, which is a lightweight messages that helps determine the device's public IP and connection path and much more. Normally, these messages follow a strict format according to the RFC and aren't meant to carry user data. But in our case, we found that Meta actually modifies this process. Instead of using the WebRTC API as intended, they manually alter the configuration data called the session description protocol or the SDP to embed the FBP cookie value inside the stun request. This technique is often referred to as SDP munging. And WebRTC standard expects SDP offers to be passed unchanged, but some browsers didn't enforce this, enabling such workarounds. This lets the native app read the cookie data directly, circumventing any sort of browser sandbox or cookie scope restrictions. Once the app receives the FBP cookie, it relays it to the Meta servers through their regular GraphQL APIs, and this process bridges the anonymous web session to the user's logged-in identity in the app. By the way, WebRTC wasn't the only way they connected both browsers and the app. Over the several course of months, Meta kept changing their ways of localhost behavior, starting off with in September 2024, they were using HTTP with one particular port. And then in November 2024, they rolled a new release on WebSocket on the same port. And then in the end of the same month, they released a WebRTC based localhost communication with SDP munging involved. And by the end, in May 2025, they were also trying to test out WebRTC with turn support as well. So over the time, they cycled through different protocols, port ranges, but the goal remained the same: link browser sessions with native apps using login and IDs via the localhost. Although both Meta and Yandex deployed mechanisms that uses the localhost interface for cross-context tracking, we found no public-facing documentations mentioning these practices, not in their SDK guides, developer forums, or change logs. What we did uncover was a series of developer forums posts on Meta's official platform dating back to September 2024, in which third-party developers reported some sort of a weird behavior. Specifically, the Meta Pixel JavaScript was issuing requests to the local host when embedded in Android web views, which are in-app browsers. And these were not isolated incidents. Multiple developers expressed concerns and confusions, and there were no official response from Meta. And one developer speaking to the broader frustration wrote, no acknowledgement has come from Meta at all on this. My support request with them got a generic response and then ignored. Now let's take a look at the different implementation of the same idea, but this time by the Russian giant Yandex. While the core mechanism is still based on the local host communication, interestingly, Yandex's approach slightly differs. Compared to the Meta's case, it's the browser that sends the data out of the server, not the app. The app just acts like a middleman bridging native IDs to the web. But let's take a closer look. Here's how the whole loop works. Many Yandex apps include the Yandex Metrica SDK, which is developed by Yandex itself. So SDKs are plugin code bundles that help developers add features like analytics. The Yandex Metrica SDK run in the background and listens on specific localhost ports. When a user visits a site with Yandex Metrica script, the script first fetches obfuscated parameters from Yandex servers, and these parameters are then sent back to the local Yandex app. And the app receives this request and replies with an encrypted device identifiers such as the device IDs and Google advertising IDs. Finally, the script forwards information back to the Yandex servers. We found a couple of things particularly interesting with the case of Yandex. First, they used a domain that resolves to the loopback address. Yandex approach relied on both HTTP and HTTPS. So the HTTP request was for the local or the loopback address, while HTTPS request to yandexmetrica.com, a domain that resolved to the same loopback address. In both cases, the browser sends obfuscated parameters to the local ports. This dual design perhaps helps conceal the true destination of the data, making it look like a standard web analytics traffic while actually reaching a native app on the same device. Second, interestingly, Yandex app do not immediately begin listening on localhost ports. Instead, they first contact a Yandex-owned endpoint to fetch configuration details. This includes a list of localhost ports to listen to and a parameter called first delay seconds, which was set to roughly 3 days. Once the delay runs out, the app silently start listening on those ports, enabling localhost-based tracking. This is significant for 2 reasons. First, it likely serves as a stealth tactic, delaying socket activation until long after app installation, making detection much harder. Second, it's clearly coordinated. Yandex controls when the socket opens and which port through the remote config. Yandex's use of local host communication channel wasn't new. It dates back to early 2017, starting in Feb of 2017, where they rolled out the HTTP support, and then on the next year, they rolled out the HTTPS support on the domain. But beyond the identity bridging, these local host mechanism introduce a secondary privacy risk, the leakage of browser history to third-party apps. Specifically, the use of HTTP as implemented by Yandex Metrica, and also in the earlier versions of Meta's channel using both HTTP and WebSocket opens up a privacy risk. HTTP requests from browser include the origin headers, so any unprivileged app listening on the same localhost port could see which websites trigger the request. That means any malicious app could quietly harvest a user's browsing history just by observing these local connections. This allows for re-identification and breaking pseudo-anonymization of data. Our test showed that browsers including Chrome, Firefox, Edge are vulnerable to this type of leakage, even when users were using through incognito mode. DuckDuckGo was minimally affected due to a few missing Yandex domains in their block list, which they quickly fixed after we disclosed it. And Brave wasn't affected. It blocked localhost requests and known trackers by default. While we did not identify any third-party apps outside of Meta and Yandex currently listening on these specific ports, the possibility remains open and the attack surface is now known. To understand how widespread this localhost behavior really is, we looked beyond just the technical feasibility. So according to BuildWith, a web analytics service that tracks third-party technologies across millions of websites, over 11 million sites have metapixels embedded in them, and 1 million have Yandex Metrica. These, these are massive deployments across sectors spanning news, e-commerce, government, and health. But those numbers don't reveal when or how the local host channels are actually used. So to understand that, we conduct our own dynamic test, crawling over top 100,000 websites using vantage points in New York and in Frankfurt. What we found was interesting. Not only are Metapixel and Yandex Metrica widely embedded, but majority of sites using them initiated localhost probing immediately before any user interaction or consent. As you can see here in the US, over 78% of Metapixel sites and over 83% of Yandex Metrica sites made localhost request without waiting for user permission. In Europe, under stricter regulations, the numbers are still comparable, over 75% and 84% respectively. These results suggest that localhost abuse is not only real, it's global, it's widespread, and potentially without meaningful user awareness or consent. As part of our responsible disclosure, we worked with major browser vendors to address the side channel uncovered in our study. And their collaboration was active and constructive throughout. Chrome was the first to deploy the defenses. In May this year, they introduced two key mitigations. It blocks the specific ports that was being used by Meta and Yandex. And it also disabled the STP munging of ICE credentials in WebRTC, the very technique Meta was using. In parallel, Chrome is also working on local network access restrictions. This feature is being currently tested on newer versions and serves as an added barrier for local host request by requiring user permissions under certain contexts. Firefox already had protection in place for blocking STP munging of ICE credentials and hence only was partially affected by Meta's local host usage. They shipped a port blocking fix in version 139 as well. DuckDuckGo amended their block list to include Yandex domains that we discovered during our research. And Brave, interestingly, was never affected. It had required user consent for local host access since 2022. But browser mitigation only goes so far. These are patches and not permanent fixes. Fully addressing these issues means rethinking localhost permissions, platform level visibility, and Android's IPC trust models. So far, everything we have shown is based on real-world evidence from Android devices. In our test, we also saw that Android was particularly targeted, and we did not find similar evidences on iOS. That being said, it's important to clarify that our focus was primarily on Android, so we did not perform an equally deep analysis on iOS. Technically, apps can spawn a local host server in iOS. However, iOS differs in certain ways. iOS imposes much more stricter background execution limits and enforces tighter control over process life cycles. Lastly, the broader concern here goes beyond Android or iOS. Localhost is accessible across a range of platforms, desktops, smart TVs, IoT systems, and much more. So while we didn't observe this attack on iOS, this underlying design pattern creates a much more wider potential attack surface. The response to our finding extended well beyond the research community. Major international outlets like us, Technica, Sky News, El País, The Washington Post covered the story, helped raise broader public awareness. One quote that stood out came from a Google representative who stated that Meta and Yandex were using capabilities present in many browsers in unintended ways that blatantly violates Google's security and privacy principles. That being said, to conclude, our findings suggest that Android's current isolation mechanisms may not fully prevent cross-context communications within localhost. We observe that native apps and websites can exchange information through this local channel without requiring explicit user permission or generating visible signals. This challenges common platform assumptions about how apps and web boundaries are enforced. Importantly, we documented real-world deployment by Meta and Yandex, where identifiers such as the advertising ID and login tokens were linked with web cookies. This demonstrates that these techniques are not merely just theoretical or hypothetical. This observation highlights that the need for re-evaluating trust boundaries on mobile platforms. In particular, the assumption that no permission means no access does not hold when local network communication is used between apps and browsers. We also found that existing defenses such as sandboxing, incognito mode, and permission prompts do not offer effective safeguards in this context. And this is in part because these defenses are largely browser-centric. Going forward, addressing these issues may require a platform-centric solutions. This includes stronger sandboxing around local host access, improving network permissioning that accounts for local interfaces, and better auditing of app-to-web interactions. That's it all. That's it all from my side. Thank you, and I'm happy to take any questions.
Okay, so we have Max in the queue. Please go ahead.
Max Mazzulla. I have two questions. First off, great work. Thank you very much. The first one is there a genuine use case for an app to listen on localhost?
Genuine use case, can you repeat that?
For an app to do localhost network traffic?
So for testing purposes, or for instance, React Native builds a server for them to serve static files, for instance. So that's one particular use case for using localhost.
Okay, but the React Native, I assume, is only within the same app?
Yeah.
Okay. Cool. And then the second one, how did Yandex do this over HTTPS?
So they had this one particular domain, yandexmetrica.com, which then resolved to the loopback IP. So essentially, when the parameters were sent from the browser to the app, they were sent, the DNS resolution happens, and then the traffic was being sent to the loopback address than to outside of the phone.
And so they ship the certificate in the app?
Yeah, within the SDK.
Thank you.
I thought I saw somebody else in the queue, but they've now disappeared. Okay, great. There was a fair bit of discussion in the chat as your talk was happening. I don't know if anybody wants to come up to the mic and just comment on mitigations that are happening in response to this. We have some of the browser implementers in the room. Basically, what was mentioned in the chat is, yeah, we're shipping even more fixes, and we are addressing this because of this work. Are there any others? Oh, yeah, please. Yeah, Martin, go ahead.
Yeah, I think the fixes, and I use scare quotes on that because I don't think the local network access thing is a good solution longer term for these things. Are all very much in chain right now. There are a few surprising things that I won't talk about at the microphone that aren't fixed in certain browsers because we don't know how to fix them just yet. And those will affect desktop browsers much more so than they will affect the mobile platforms. As to Max's point, there's no reason for an application to be using localhost to communicate with other apps. You mentioned debugging. Sure, people doing debugging things can break all sorts of things in the security of the system, but apps are given ways to communicate with other apps on these platforms through the front door. This is obviously going around the back, and that's not there's no legitimate reason for them to need to do that because there are things like on Android, at least there's intents and various other things that you can use to pass messages. So it seems to me like there are some platform level changes that you can make on those restricted platforms that would improve the situation considerably. But the problem exists on desktop platforms as well, and so we need to look into that a lot more.
Okay.
Yep, I agree to the point as well, and there are existing IPC models across within Android, like indents and whatnot, for app-to-app communication. And also in our test, we found that Android was the one particularly targeted, so we didn't see that happening in the desktop yet.
I want to follow up on just one more point that I saw in the chat, which was, were there any legal implications for companies using these side channels? And the comment here was they got strongly worded emails from Google, but that's all. Is that the case?
So we are technical researchers and we don't have legal background, but all we can say is like the regulators are aware of this.
Right.
And
But neither of the apps have actually been pulled, is that correct?
Sorry?
Neither of the apps have been pulled.
No,
No,
they're still in the Play Store, and the behavior have stopped right after the Ars Technica publication.
Yeah.
So yeah.
But they're still out there today. So okay. Thank you very much for doing this work and for presenting here. I appreciate it. You're a local, aren't you?
Yeah.
Yes. So if you have
Thank you for
Madrid
inviting
local.
as well.
Thank you. That's great. Thanks, everyone. Okay. All right. So for our next presentation, bear with me for a moment because we have a remote presenter, but we're going to play the presentation as a video, and then we will do a live Q&A after that. So I'll just switch over to the video playing. Okay, so let me see if I can do this. Okay. If I can. This won't let me switch. Nope, it does not want to let me. Okay, there we go. Okay. All right, here we go.
Hi everyone, my name is Alicia Ukani, and I'm a PhD candidate at UC San Diego. Today I'll be presenting our work, Local Frames, Exploiting Inherited Origins to Bypass Content Blockers. This work was done in collaboration with Hamid Haddadi and Peter Snyder at Brave, as well as my advisor, Alex Noren. In this talk, I'm going to show you how most websites can easily bypass popular content blockers, and that over half of popular websites currently have the capability to do so. I'm going to start with some background about local frames, origins, and content blockers, before diving into the 4 core capabilities of popular content blockers. Then I'll discuss how we can actually evade these capabilities through local frames, and then discuss our measurement study of local frame prevalence before concluding. So let's start with local frames. A local frame is simply an iframe with a non-standard source like about blank. Now, normally iframes are used to pull in third-party content, but here you can just think of it as a wrapper, where you can dynamically add your content and then have a very useful isolation mechanism. Local frames, like all iframes, get an empty HTML document, no CSS rules, clean JavaScript environment, and so this is great for isolating certain code in your first-party website from the rest of your content. Now let's get into origins. An origin is defined as a protocol, hostname, and port. So for example, the origin of https foo.com/bar would be https foo.com with an implied port of 443. Now, origins are often discussed in the context of the same origin policy, which protects users from potentially malicious embedded content by saying only content with the same origin can access each other. But we're going to consider it in a slightly different context, which is content blocking. Often content blockers are deciding whether to allow or block a certain network request by determining whether it's made in a first-party or third-party context. Now, in order to determine that, you need to understand the origin of the request source and destination. Now, normally, the origin can be derived from the frame's URL. So in that example I showed you with https://foo.com/bar, we could just use that URL to derive that origin. But it's a bit more complicated for local frames, because local frames actually inherit the origin from their parent frame. So let's go through an example. Let's say we're browsing on foo.com, and we have an iframe pulling in content from a third party, bar.com. If we write some JavaScript code and execute window.location.hostname and window.origin, they both return the same value, which is bar.com. So it might be really easy to think that these two properties are equivalent. But if we consider a local frame and we execute window.location.hostname, we actually get an empty string, because what's the hostname of that blank? However, if we were to execute window.origin, we would then inherit the origin from the parent frame, which is foo.com, and get that value. So this just shows how easy it is to handle local frames incorrectly. If you're not thinking about them, you would think these two properties are the same. And we find that many content blockers make this exact same mistake, and so they can be bypassed in local frames, but we'll talk about that later. Now let's actually talk about content blockers. Content blockers are tools that can hide ads as well as any unwanted content. They can block tracking scripts, reduce mobile data usage, and they're extremely popular. I've listed a few of the top content blockers here. So we've analyzed the capabilities of content blockers and grouped them into 4 different categories, which I'll now dive into in more detail. To illustrate these capabilities, I'm going to walk you through an example website. We can see that it has an ad on the left-hand side, and then as also a tracking script. The script first needs to be requested from another website, track.com, which will then return the script, and once it loads and executes, it'll perform canvas fingerprinting. Here, canvas fingerprinting is an example of a just privacy invasive behavior, and it works by accessing the JavaScript Canvas API to render an image that is often hidden from the user. And on different people's computers, this is going to generate a slightly different image, and so it can be used to generate a unique identifier. So let's start with the first capability of content blockers, which is request blocking. If a content blocker is installed and wants to protect this user's privacy, they can simply prevent the website from requesting this script, so it never gets returned and never executes on the page. So this is very effective, but also a little heavy-handed. Let's say that script also...
Okay, I think we lost the screen share. Let me try again. Okay. It's thinking about it. Okay, let me try it once again. Stop it and start it. Okay, I'm just going to try and... Nope. My Meet Echo has decided to freeze with a... Okay. It does not like screen share. Okay. Alicia, do you want to just try sharing your screen if you have the video? It's just graying. It's just freezing and graying. I'm just trying to switch back to slides and then back to screen share, and it's just gray. So I may need to rejoin. Okay. Oh, here we go. Let's try one more time. And Meet Echo folks were here. Yeah, we. Do you have the Shivan, do you have the link to the video? Could you share that? Or Alicia?
Yeah, I think Alicia shared it on the chat. It's the YouTube link.
Yeah.
Let me.
Hi, yeah. I requested screen share as well, but it's saying that all of the media's slots are
Yeah.
taken, so I'm not sure if that's working.
I think my Meet Echo session is somehow hogging it. So I'm tempted to leave the room and come back in.
I just granted her access.
Thanks. So I'm not sure if the audio will work, but I will try it and we can hope for the best. But please let me know if the audio isn't working.
And we were 5 minutes into the talk. If you want to.
And the audio isn't coming through.
Yeah, I'm not sure how to get the audio to work with the screen sharing, unfortunately.
Yeah. Okay, let me see.
Worst case, I can try and start just presenting and share the slides, but it is 3 a.m. here, so that's why I'm trying to do the recording.
I'm back in with a new session. Let me just see if I can share my screen. Back in new session. See if I can share my screen. Okay. Session. Share my screen. Okay. Okay. Share my share a window. Okay. Share this window. Share a window. Share this window. Oh, I need to be muted. Sorry. Okay, that's better. Okay, let me just scoot back a little bit. And we will try again.
Blocker is installed and wants to protect this user's privacy, they can simply prevent the website from requesting this script, so it never gets returned and never executes on the page. So this is very effective, but also a little heavy-handed. Let's say that script also included some important variables that the page actually needed to access. Now, if we never let the script execute, then we're not going to ever define those variables, and the page may even break. So this is the motivation for the second capability, which is called resource replacement. Instead of outright blocking that script, we could redirect it into a benign version. So for example, we could change this network response to have it return an empty JavaScript file instead of this tracking script. We could also redirect the script into another version that defines those important variables that the page needs to access, but not actually perform that canvas fingerprinting. The next capability is called scriptlet injection. Scriptlets are pieces of custom JavaScript code that these content blockers inject into the page. So scriptlets can do a variety of things. They can remove cookies, they can disable access to certain JavaScript APIs. And so in this case, we could prevent access to the Canvas API and therefore prevent Canvas fingerprinting from taking place. Finally, the last capability is cosmetic filtering. This capability uses HTML and CSS selectors to find something on the page and simply hide it from the user's view. So for example, we can make this ad disappear. So now let's talk about how these capabilities can actually be evaded through local frames. So in our work, we designed a bunch of test web pages that specifically isolated these capabilities and tested whether they behaved correctly inside of local frames. So for request blocking, we made a test page with different local frames, and in the local frames, we tried to request a certain resource. Then we systematically downloaded different content blocking tools, added filter list rules to try and block that resource from being requested, and checked if those requests were actually blocked. For resource replacement, we chose a representative example of AJAX asynchronous requests to be redirected. So again, we created a bunch of AJAX requests inside local frames. We set filter list rules in different content blocking tools to try and redirect the response of that request, and checked whether that redirection was actually successful inside of local frames. Similarly, for scriptlets, we chose a representative example of setting a property of the window object, and we checked if that window object was successfully set inside of local frames. Finally, for cosmetic filters, we checked that if we try to hide an element in a local frame, is it actually correctly hidden? So through this analysis, we found 19 different vulnerabilities across 6 different content blocking tools. We found that all of the tools that offer cosmetic filtering as a capability had a vulnerable offering. We also found that all of Brave's iOS protections could be bypassed through local frames, and later we'll talk about why Brave iOS was vulnerable to request blocking evasion. Now, we disclosed all of our findings to the affected parties. So our work led to patches in Brave, Apple, AdGuard, DuckDuckGo, and uBlock Origin Lite, where we collaboratively worked on that. And so ultimately, 15 of the 19 different vulnerabilities that we found have been patched. So now I'm going to go into a few case studies of some of these patched vulnerabilities. Let's start with AdGuard. AdGuard was really interesting because they computed the origin of a third-party local frame to be the first-party website. Now, this has 2 main consequences. The first one is evasion. So all the rules that were meant for the third-party website were not being applied to that third-party local frame. So this means that any tracking resources that were requested in the frame would not be blocked. The second consequence is potential breakage. So all of the rules that were meant for the first-party website were now also being applied to this third-party frame. And so it's likely that the developers did not test those rules on this third-party website, and this could cause some breakage. In addition, AdGuard had this miscomputation for scriptlets and cosmetic filtering. And scriptlets are really powerful, and they can disable standard web development tools like event listeners. And so the possibility for breakage is magnified. The next case study is the Safari Content Blocker API. This API was introduced by Apple. Apple was concerned about apps being able to view network traffic, but they still wanted to allow content blocking apps, such as on iOS and Safari extensions. And so Apple created this API that would let these extensions define their own filterless rules, but then Apple would actually enforce them. We found that this API was vulnerable to evasion for cosmetic filtering. And so this means that all of the apps that were relying on this API were also vulnerable. And so this could have significant downstream effects. Our next case study is Brave. Now, Brave is a privacy-forward browser that tries to comprehensively protect users from tracking. But the more code you write, the more code complexity you have, and therefore the more opportunities for evasion you can also have. So as an example, Brave iOS was using that Safari content blocking API to protect users from standard network requests to trackers. But that API did not cover asynchronous network requests. And so Brave introduced an additional code path to protect users from asynchronous network requests to trackers. But in that code path, they had a bug where they weren't properly computing the origin of these requests, and so they were able to be evaded through local frames. Our last case study is DuckDuckGo. Now, DuckDuckGo actually couldn't be evaded. They correctly blocked network requests to trackers that were made not only inside local frames, but also local frames nested inside each other, so that's great. But they still had a bug. DuckDuckGo has a feature where they report to the user the number of tracking requests they blocked. So even though they would block these requests to trackers inside a nested local frame, they wouldn't actually report that back to the user. And so the user may not know about the privacy harming behaviors of the websites they visit. So this just goes to show that even if a capability can't be evaded, there are still so many subtle ways to incorrectly handle these types of frames. So I'll again note that all 4 of these case studies have been patched due to our work. Let's get into the last section, which is our measurement study of local frame prevalence. We conducted a large-scale measurement study crawling almost 22,000 websites from the Trenco list of the top 1 million most popular websites. We measure not only how many local frames there are, but also the behaviors happening inside them, such as the network requests they make, the JavaScript API calls, including fingerprinting-related ones, and the HTML elements created inside them. We found that local frames are extremely widespread. We found them on over half of the websites we crawled. And also that 62% of websites with local frames were making requests to tracking resources inside of those local frames. And this represents 14% of all websites we crawled. In addition, over a third of websites with local frames were making calls to fingerprinting related APIs inside them. And lastly, we looked at which third-party entities were creating third-party local frames, and we found that they were primarily analytics and advertising companies. So to conclude, we found that local frames are extremely widespread and could evade content blockers. But our work has led to patches in Safari, Brave, AdGuard, uBlock Origin Lite, and DuckDuckGo. Now, what I hope you take away from this talk isn't that we found some cool new evasion technique, but really that the web is complex, and developers need help in navigating this complexity. I think it's very understandable to make these subtle mistakes, but the more support and resources we can provide to these developers, the easier it will be for them to handle these sort of complex cases. So thank you so much for listening. You can find links to our paper as well as all of our code and data, and feel free to contact me if you have any questions. Thank you.
Okay, thank you very much, virtual Alicia, for giving us a video presentation, and also for real Alicia for being available for questions. I left Ignacio in the queue. I think his question was for the previous speaker, but I wanted to double check. If I don't hear anything, I will assume that was the case. Okay, I'm going to remove you from the queue, and we have Steve Hill in the queue. Please go ahead.
Are the local frames being used by the advertising networks specifically because they're bypassing these blockers, or is that just a side effect?
That's a great question. It's very difficult for us to infer intent because these are also just very much a standard web development tool, and there's a lot of benign use cases for them. When we did start looking into some of the content that these companies were loading into frames, they were used for a variety of things, such as ads, but also like CAPTCHAs. And so I think it's kind of impossible for us to right now infer whether they were actually trying to evade these or just use it for that kind of clean environment and isolation.
Okay, thank you.
And Shivan?
Thanks, Alicia, again for presenting. Just wondering, you mentioned that most of the vulnerabilities you reported were patched. Just wondering why you think the other ones were not?
Yeah, great question. So I guess one anecdote I can give is that we found that uBlock Origin Lite could be evaded for cosmetic filtering. And we talked to the maintainer of this project about it, and he said that he wanted to wait until this became more widespread and users started reporting it as an issue because he believed the fix would have some performance overhead. And so it's possible that it will get fixed in the future, but just right now he wanted to wait until it becomes a more severe problem.
Thank you. Any more questions? If not, Alicia, I know it is the middle of the night for you, so we thank you for being up to answer those questions. And if we can show our appreciation for the speaker, that would be great. Thank you.
Thank you.
Okay. Okay, so our next talk poses the question, is fully homomorphic encryption ready for now, developments and standards? So let me just give you, okay. Do you want to just test your slides, progress? Yep, you have control?
Yeah, yes, it's okay.
Okay, lovely, that's great. I will hand over to our next presenter then, thank you.
Thank you for the introduction. Hello, everyone. I'm Xianhui Lu from China. I'm very happy to share the developments and the standard, the proper progress.
Could you just speak slightly louder? It's a little quiet in the room.
Okay. It's now
Thank
okay?
you. Yep,
Yeah,
that's much
yes.
better, thank you.
Okay. Thank you for the introduction. Xianhui Lu from China. I'm very happy to share the developments and the standard of FHE. And I hope with my data and information, and everyone from different areas can answer, can give your own answer that is FHE ready for your applications. Now I will begin. Uh, the main part of my talk is I want to introduce the 4 aspects of the development of FHE. The first is the evaluation mode, and the second is the bootstrapping, which decides the performance of the FHE mostly. And the third aspect is transferring, which can be used to reduce the bandwidth. And finally, is the homomorphic processor intersections, which can provide a very user-friendly interface. And before the development details, I'll first give some warm-up. And first is the definition of FHE. So FHE is a very powerful and special encryption schemes, and it can be used to compute, support the computation on encrypted data. Suppose I have several messages M1 to Mn, they are all encrypted, and I also have a target function f. Then I can compute on the encrypted data and get another new ciphertext, which is just the encryption of fm to mn. Okay. So what can we do with the help of FHE? The simple answer is we can do privacy preserving. And suppose the user have some data X want to process, and the target function is F, and he can send the encryption of X and also the target function F to the cloud server, and the server can do the computation on the ciphertext and send the ciphertext back to the user, and the user can decrypt and get the results. So that's the main use of FHE. FHE has a very long history of research. It is proposed in 1978 and have a 47 years old research story. But in the first 31 years, that it is remains an open problem. And the first scheme was designed till 2009. And from that on to currently, there are 16 years research story. And in the first 16 years, and in the first 8 years, several basic schemes are designed. For example, the BGV, BFV, and the CGGI, and also the CKS. And in the recent 8 years, several optimization skills and techniques are proposed to speed up the performance of FHE. And currently, we have very practical schemes. And also the standardization and implementation open source library are published. Okay, next. Before the detailed data, I will give an oversight of the performance evolution of the FHE from the first scheme that was proposed in 2009, and its implementation was published 2 years later. In this implementation, the most time-consuming algorithm, that is the bootstrapping, takes about 30 minutes. And currently, we have different kinds of bootstrappings. For example, for the bootstrapping of gate bootstrapping, that is, we only bootstrap a single gate, and it can be completed in 1.8 milliseconds. So it's about 1 million times faster than the original bootstrapping. And for the case of circuit bootstrapping, and it's about 100,000 times faster. And if we want to bootstrap 8-bit block, and it is about 30,000 times faster. So that's an overview of the performance evolution. And currently, you can test the different kinds of performance or build your own demos based on many open source libraries. For example, we have libraries of BDV, BFA, and CKKS in the CU library, the IT library, and the HAND library. And you can also test the CGGI or the TFAT scheme in the TFAT Rust library. And you can also test the fast circuit bootstrapping in the Light FAT library. Okay, that's an overview. Okay, now let's begin the development of the 4 aspects. The first aspect is the evaluation mode. There are 2 basic evaluation modes for FHE. The first mode is high throughput mode. In this mode, the data are embedded in a polynomial. For example, we can embed 2 to the power of 14 integers to a polynomial, and the target function is divided into several polynomials. And after each polynomial, after the evaluation of each polynomial, we need to bootstrapping to refresh the ciphertext. And the second evaluation mode is the low latency mode. In this mode, we only deal with a single bit each time, and the target function is represented as the binary circuit or a lookup table. Okay, based on these 2 evaluation models in the recent years, there are new models to combine these models together. For example, for the BDV, BFA, or CKS schemes, which are originally using the leveled model, and currently they can also deal with the lookup table algorithms. And with this development, it is very useful for the in the case of neural networks and even the large language models. And on the other side, the TFAT and FATW can also provide the vectorized model. For example, we can use the homomorphic neural theorem transform or the tensor ring algebraic structures to do the SMMD in the computations for the TFAT schemes. And even more, we can currently we can switch among all the different ciphertexts. For example, the BDV, BFV, and even the variant of FATW, and even the N-true type FAT schemes can be all switched among different models. And with this practical switching algorithms, we can build a hybrid evaluation mode for our target functions. And now let's see 2 examples of using different models. The first model is the first application is used in the feed-forward block inference, which is the building block of the BERT's model. And there are 2 kinds of computations. The first is a matrix multiplication, and the second computation is the GLU function. And to evaluate these models in the original evaluation mode, we need the multiplication depth of 30 levels, and which will result a very large modulus. It is about 1,700 bits. But if we use the new models, we can do that algorithm in about 13 multiplication depths, and the modulus can be reduced to 600. And with this speed up, the overall computation time can be speed up by 100 times. And the second example is in the case of simple neural networks. For example, the facial recognition or the speaker verification. In this case, we only need a very simple convolution neural networks. And in this case, we can cross between the linear mode and the nonlinear mode by using the switch schemes. And based on this model, we can complete the computation of facial recognition in about 0.2 second, and the speaker verification in about 0.6 second, which is very practical for real-time applications. And the second aspect is about the performance of bootstrappings of different kinds of bootstrappings. And the first example is for the performance of Git bootstrappings. And in the recent years, there are many skills to speed up the Git bootstrapping performance. For example, we can co-design of the parameter and the AVX instructions. And we can also use the more compact entry structures to reduce the times of polynomial multiplications. And we can also use the better noise management to reduce the parameter size. With these skills, the performance of Git bootstrapping can be reduced from less than 1 second to the currently we can to less than 2 milliseconds. So it's about 500 times speed up. And for the case of circuit bootstrapping, and we can also use the more simplified framework, and we can also use the simplified split FFT algorithms, and we can also use the noise management by pre-computations. And by combining these skills together, the performance of circuit bootstrapping can be reduced from 137 milliseconds to 30 milliseconds now. So it's about 10 times speed up. And for the case of functional bootstrapping, and we can also use new algebraic structures to overcome the neg-cyclical limitations. And we can also use the outer product tree to reduce the time of high precision FBS. And we can also use the private preserving FBS for private functions. And by combining these techniques together, and we can speed up the functional bootstrapping by about 1,000 times. Okay, now let's begin the third aspect. Besides the performance, the bandwidth is one of the other challenging for the FHE. Currently, we can use the transciphering technique to minimize the bandwidth requirements of FHE. Briefly, it means in the communication and the storage, we can use the symmetric algorithm to encrypt the data. And for example, we can encrypt our data by AES algorithm, and in the cloud server, it needs to firstly to do a homomorphic decryption of the AES and then do other target functions. And based on this scheme, in the recent years, for example, the transciphering of the AES schemes is speed up very large times. For example, for the high throughput model, and the first implementation is about 240 seconds, but currently we can do, and the amortized function is 2 seconds. And currently the amortized time is 14 milliseconds. That is in the first implementation, we can only embed about 120 blocks of AES ciphertext, but currently we can embed 2 to the power of 15 or 14 AES blocks in a single ciphertext. And for the low latency implementations, and currently we can complete the transciphering of AES in about 11 seconds. So it's about 20 times speed up. And the through output is about 16,000 times speed up. And the final aspect is usability. Fully homomorphic is very complex and hard to use. Even with many open source libraries, it is also hard for engineer to develop FHE-based applications. But in the recent years, there are many FHE compilers are developed. And For example, we can design the FH instruction set, and based on this instruction set, we can build a FH virtual machine. And this is a very friendly interface for engineers. And for example, we can build this instructions based on the functional bootstrappings, and it may take about uh, 48 milliseconds for the end instruction. And if we build this instruction sets based on the circled bootstrapping, and we can get 30 times the speed up. And for example, we only need about 36 milliseconds. And for the end instructions. Okay, finally is the progress of standardization. And in 2019, the partial FHE schemes are standardized in ISO IEC. And in recent years, from about 2022, the FHE are standardized in the ISO IEC. And in about 1 or 2 years later, I think this standard can be completed. Okay, finally, let's go back to our main question. Is FHE ready for your areas? And we have different friendly models, and the performance is not about several milliseconds, and the standardization will be completed in about 1 or 2 years. And I think you can share your mind of whether FHE is ready for your applications. Okay, that's all. Thank you.
That's great. Thank you very much for that excellent overview of the current status of homomorphic encryption. I think we have one, I'm just going to remove, we have one person in the queue, Lee Lun, if you'd like to go ahead, please.
Yeah, thank you for the professor, very impressive work on the performance issue. I have, we have a group who is very interested in the homomorphic encryption in IETF and IRTF. So my question is based on, so first I want to ask about the quantum safe. So is all the FHE algorithm used you introduced just now are considered be the quantum safe because I think many of them are the lattice based. Any answer or quick answer I can get or you can introduce. And the second question I want to ask is, we trying to sort of figure out how the protocol design for this homomorphic encryption. And so compared to the public key, maybe the computation key you just mentioned, how it should be distributed. Usually we, like the public key, we use the PKI system. So what's your view about how to distribute the computation key? That's true, thank
you. Okay, let's go to first question. And currently, if you are talking about fully homomorphic encryption, then they are almost all designed based on lattice hard problems. So currently, they are thought to be quantum resistant and quantum safe. But if you are talking about the partial HE, and they can also be designed based on the factoring problem or even the discrete logarithm algorithm, so they are not quantum safe. And for the second question, it's a very complex question, and so currently we only consider the performance and in the single machine. But if you will use in your real application, you need a key management protocol. For example, you may need the proxy re-encryptions or the threshold encryptions, and or even the MPC algorithms to deal with the key management.
Okay, thank you.
Thank you very much. If there are no other questions, then I think we can just thank our speaker, please.
Thank you.
So we do have some time left, so we will go to our time permitting presentation.
Okay.
Okay. So let me just give you the slide control. Okay, and I think if we can take 10 minutes of presentation, and then that will still leave us a little time for questions, that would be great.
Okay, thank you very much.
Okay, please go ahead.
Yeah, hello everyone. This is a presentation from Alipay and Hong Kong University of Science and Technology. So here the presentation title is about privacy preserving computation, use case and problem statement. So as we know that data becomes more and more important, and some expect that AI will consume all the data required. So in the future, how to realize data collaboration between different companies is becoming more and more important. Then, securely realize the collaboration, protect the data confidentiality and privacy is the key to success for data collaboration. So here we will list some use cases for the data collaboration. The first thing is about a data set intersection. So for example, if a company have data that users who Twitter or not, well, another company may have the users who like to video games. Then they want to calculate the users who Twitter a lot and likes the video games, but they don't want to share additional information. So in this time, in these scenarios, PSI data, privacy data intersection is the technology can realize that. So for example, there are a lot of PSI algorithms. So here ECDH PSI is an example that may have been widely adopted by companies. For example, Alibaba, ByteDance, and etc. And then there's another piece is that private key value query. So for example, if company A have a data set of the users credit, and then company B they want to query that company B want to check Bob's credit, but company B don't want A know that he is interested in Bob, and then in this user case. So for example, the homomorphic encryption can realize that. So the solution we had, Professor Lu has introduced the homomorphic encryption. So we have some user cases in some medical search system that using HE they can realize 1 million matching queries within 5 seconds. And then the third case is that private inner production. This is the scenario that the company A and the company B they want to calculate their joint inner multiplication, but they don't want to expose their own data. So this is an example that this is an example that we have implemented that 1 milliseconds can realize the inner encryption. And so this is the fourth case that have collaborative machine learning. And for example, company A have some features, company B have some other features. They want to have doing modeling to, for example, the fraud detection, the credit assessment, etc. Then during the machine learning, they don't want to expose their their data to each other. Then in these scenarios, PSI, multiple party computation, MPC technologies can be used. So we have some examples that like 10 million users, 10 features, they can finish it within 1 day for the fraud attacking user case. So as we can see that we have shared 4 different user cases: joint querying, joint modeling, joint data section, etc. So in all of these user cases, they are concerned. First thing is the security. So all the data confidentiality that no data owner want to expose or leakage their data to each other. And also is that the output result, they want to be acceptable to the authorized party. And besides the security, they may have some functionality, performance. So, for example, how to realize how to satisfy the traffic requirements within the required time. So, so here we think that we can see that joint data collaboration based on the privacy-preserving computation, they have been realized and implemented in a lot of use cases. So we think that it's an interesting topic that maybe we can trigger some discussion about how to utilize privacy-preserving technologies for cross-company data collaboration. So for example, the PSI technology, the homomorphic encryption, the further learning, trust the execution environment, etc. So here we have triggered some proposal about the PSI, and so here is some ongoing research we are doing. We have doing some PSI, some PIR, and also they have been adopted by some conference for the paper publication. Yeah, that's another kind of that's the machine learning related discussion and the papers research work. Yeah, thank you.
Thank you very much for that. We have Martin in the queue. Please go ahead.
Yeah, Martin Thompson, thanks for the presentation. These are all very interesting questions to be asking. I think probably the most important question to be asking is not can we do these things, but should we do these things? As someone who works in MPC once reminded me, MPC can do anything, but you have to have some way to decide what it does. To sort of poke on that a little bit with the concrete examples you gave, you're talking about private set intersection, which is an interesting problem, academically, but if you look at these scenarios, there are cases where, for instance, 2 large companies that I have an account with, knowing that I have an account with the other company is potentially a privacy violation from my perspective. it breaks contextual integrity, which is a property that we kind of value. So knowing what is acceptable and what is not is perhaps probably one of the most important things to understand in this context. Thankfully, in a lot of places, like the one that I find myself in, the laws are extremely short-sighted when it comes to things like these protected computation or privacy-preserving computation techniques, and they essentially forbid them, as I've learned. And they don't distinguish between this form of computation and any other form of computation. And so, to a large extent, we can rely on those laws to make it impossible to do these things, even if we might think that the functions are acceptable. So, coming to conclusions about what is acceptable is only step one in a much longer journey of making sure that what you can do is acceptable. And I understand that this is a different situation in different countries, but it's something to keep in mind.
So I think one question we have is that there are proposals that this research group would be an appropriate place to try and formalise some of these primitives. And I think that's a question we would put out to the list and to Dirk as to whether that is the case. This is the home for this or not. And I think that's a discussion we should have on the list. If that's okay. Okay, thank you once again for your presentation. Thank you.
Yes. May I echo to Martin's problem or yeah?
Yes, please. Yeah.
Yeah, I think privacy preserving computation is not a. We have tried some use cases, so I think they are not trying to solve the law problem. They are trying to solve the secure problem. To solve that, companies they want to share and they are safe to share their data. For the laws, if there's some laws, I think you just follow the different countries' law. Yeah.
Yeah.
Yeah, I was going to say, in these situations, a lot of the use of these computation techniques is to protect the commercial interests of the companies involved, not the privacy of the people. And this is something that is often mistaken. It's often presented as a privacy thing, where privacy can sometimes be a secondary effect of it, but it's mostly the commercial interests that are being protected here.
Yeah. Yes. Thank you.
Thank you for that. With that, we wrap up the meeting for today. Thank you, everyone. I hope you have a good rest of IETF and safe journeys home. Thank you for coming.
Thank you. Bye-bye.
Thank you for your presentation.
Bye all.
我其实并不是。
要不然你麦再开着。
啥？
麦关了吗？